First of all, a reminder from single variable calculus that we have a something we call a probability density function, and that function, also known as a PDF for probability density function, means that the function itself has to have the area under the curve from negative infinity to infinity. The total area has to be 1. And when I say area under the curve, of course, I mean above the x-axis as well. And that's the other property, is that the function can never be negative. Okay. And so based on those, we have a very special distribution, the normal distribution. And here's how it's defined. In this particular case, it's an exponential function here, where the sigma is representing the standard deviation, and the mu symbol here is the mean. So the mean and standard deviation you'd be familiar with some statistics. And the most common form of this is our standard normal curve, where the mean is 0 and the standard deviation is 1. So if we plug 0 in for the mean and 1 for the standard deviations, then it becomes this distribution here. And I would like to just quickly show you why this in fact has to be a probability density function. First of all, it's exponential, it's never negative, so it meets that criteria. And then we have to show that the entire area under the curve from negative infinity to a positive infinity is 1. So this is what we're needing to show then, show that that's the case. And we're going to do that just by working out this integral here. And first, a little substitution. If we let, well, I'm going to let w squared be the x squared over 2 in the exponent here. In other words, w is really the x over root 2, and then we get a dw to be a 1 over root 2 dx. And so that's going to transform our integral here. We'll get this 1 over root 2 pi, and our integral negative infinity to infinity, with our dw being 1 over root 2 x, we get a root 2 dw, and this becomes e to the negative w squared. So let's just pull this out front, this root 2, so it'll cancel with the root 2 there. So we get 1 over root pi, and this integral negative infinity to infinity, e to the negative w squared dw. And we showed that this integral, we showed that in fact that is the square root of pi. And you can go back and take a look at the notes from last week, and the root pi's cancel and we get 1. So it is a PDF. In multivariable, we have joint density functions, and it's a similar idea, of course. It's just we're saying we can have more than one variable here. It could be beyond the x and y, could be multiples beyond that. But again, the two criteria are essentially the same, that the function can never be negative, and that the total, in this case, total volume under the curve is 1. In other words, the total iterated integral has to be 1. And then we can find the probability then for any particular value. Say the x value is going a to b, the y value is c to d. Of course, the probability that you'd have something in those regions would just be integrating in that region. And you could have more complex stuff as well. It doesn't have to be just bound to that. Let's consider if we have joint density function that the two variables are independent. Now, in statistics, the independence is a very important property to be able to have. You don't always get that. But if they are independent, the calculus turns out very nice as well, because that means that rather than writing the function as a function x and y, we could write them as a product of two independent functions, a g of x times an h of y. And if that's the case, then integrating to find the probability on a particular region here, we can write this as the separate integrals, for the x integrating the g function and for the y integrating the h function. Just makes it a little easier. We'd like to determine whether this particular function is a probability density function. So we'd like to find out, first of all, show that the function itself is never negative, and I should say that we are interested only in this region here. Assume that this function is 0 everywhere else except for this region. So I've graphed this region down here to give you a visual here. The x value is bigger than 0, the y value is bigger than x, and everything's less than or equal to 2. So first of all, because the y's greater than or equal to x, then this function is in fact always greater than or equal to 0, so it meets that first criteria. So the second thing we want to check is that iterated integral here across the region, is that actually equal to 1? So that's the next thing we want to check. Let's see, should I do x and y? Sure, let's try that out. So if we go x then y, the x values will integrate from 0 until we hit the line there. So we're going to integrate from 0 to y for the x values. Then the y values we integrate from 0 to 2. Okay, so integrating 0 to 2, 0 to y of 6y minus x dx dy. So first we'll do this inside piece. So antiderivative of 6y with respect to x will be a 6yx, and the antiderivative of negative 6x will be negative 3x squared. Again, this is all with respect to x, and then the x variables are going from 0 to y, and we still have to do the outer integral when we finish that. So let's plug stuff in here. So put in the y. This will be a 6y times y minus 3y squared, minus plug in the 0, and you get nothing more. And that simplifies rather nicely to a 3y squared dy. And that integral, antiderivative, is a y cubed, and that's going from 0 to 2. And plug that in, we get 8. And notice that is not 1, so that means we do not have a probability density function. In this example here, we've got xy e to the negative x minus y across this region where x and y are both non-negative. Assume it's 0 everywhere else. You can quickly see that, of course, this function itself is always greater than or equal to 0, so that meets that first criteria. And then we want to check the integral, in both cases going 0 to infinity, of this function xy e to the negative x minus y dx dy. Something I'd like to point out right away on this one is, of course, e to the minus x minus y could be written as e to the x times e to the negative y. And so we can actually, these are independent. And if they're independent, we can write them out as two integrals being multiplied together. So our first integral, and then multiplied by our second integral, 0 to infinity, of y e to the negative y dy. Now notice these two integrals here are really exactly the same thing. So we can reduce it down to one integral squared. Okay, so save us a little bit of work here, integrating 0 to infinity of x e to the negative x dx. We've got to rewrite this improper integral, limit as b goes to infinity, from 0 to b of x e to the negative x dx, and it's all that squared. And just to do this integral, which I know you've done many times in the past, but there's a substitution here for it. And so you do the substitution, I'm sorry, it's integration by parts, not a substitution. And we get this limit as b goes to infinity of, we get negative x e to the negative x minus e to the negative x from 0 to b. Oops. And again, the whole thing squared. And when we stick stuff in here, limit as b goes to infinity of negative b e to the negative b minus e to the negative b, alright, crazy, minus, plug in 0, 0 minus e to the 0, and everything squared. And when we take these limits, I'm not going to go through the details, but that ends up being 0, that's 0 minus a negative 1, and everything is squared. Oops, squared's over here, and that's equal to 1. So we do in fact get a PDF function.